at this point, we've talked about lots of things about energy, including various energy types. It's time to zero in on why we think energy is such an important topic. It turns out that if you identify all the energy that exists before something interesting happens, and you identify all the energy that exists after it happens, it turns out those quantities are the same. Another way of saying that is that energy can't be created or destroyed. So there's a lot of nuances to that statement, and specifically, they relate to where is energy? Is it remaining in an object or is it going somewhere else? So we'll have to kind of visit the details of that. But broadly speaking, that is true for the universe. And if we really are thinking about all the energy in the universe before something interesting happens and after something interesting happens, we can actually write conservation of energy very simply. Energy original equals energy final. So that ends up being the basis of an equation we can use to start solving pretty interesting problems as we convert between the various types of energy you identified. That's not this first lesson. In this first lesson, what we're going to do is we're just going to try to identify the different types of energy that objects have in certain situations. So what you're going to do for each of these is you're going to write EO equals EF, and you're just going to list the energy types you think exist before the event happens and after. We should look quickly at what we've identified as energy types. This was part of our initial energy discussion, which is probably different in every class. But here's what it looks like for a typical one. So we've seen that there's energy of motion or kinetic energy. There's this idea of stored energy, potential energy, which could be the energy that's stored as you lift something up and make it go higher. It could be the energy you store in a rubber band as you stretch it. It could be the energy stored in food or fuel, or stored in our body as ATP. So there's lots of different types of energy. So what you're going to do here is just list what you think there is before and after. So using the energy types we just saw, I would say a roller coaster at the beginning has potential energy. And at the end, it has kinetic energy. And this equal sign is still there. So in other words, what we're saying is we're transforming the original potential energy it had into kinetic energy. So go ahead and do these for the others. And then we'll come back and talk. So here's my answer key, and hopefully it makes sense to you. Notice I went back to our example and I added the word gravitational here. Potential energy generally is how we store energy, and actually energy stored in chemicals like gasoline or coal, that's a potential energy as well. So I specified this potential energy was the energy we get by lifting something up and storing it up high. Just a couple of things worth mentioning. If we're talking about the entire universe, most times we have an energy transformation, it becomes more than one energy type afterwards. For example, nuclear power plant, the energy that's stored in the uranium atoms, a lot of it becomes electricity, but a lot of it becomes heat. And notice that that's true for coal-fired plants, that's for natural gas power plants, it's for your car. And typically we need to have some way to get rid of that heat, as it's kind of a wasted type of energy. For example, this is why Millstone was built on Niantic Bay, because Long Island Sound was a convenient place to put the thermal energy that the power plant produces as a byproduct of making electricity. So most energy transformations, the energy doesn't always go to what we want it to. And we deal with that by talking about a topic called efficiency. Efficiency is really a measure of how much goes into the energy type we like. But this is really the heart of this unit, is tracking what kind of energy do we have before and what kind of energy do we have after. On this worksheet, you're going to do exactly what we just did before. You're going to write EO equals EF. but you're probably going to have more trouble with this. I've deliberately kind of picked these situations so that it's not obvious where and what type of energy we have either before or after for some of them. Do the best you can on this, just like before, but if you can't figure out where the energy is coming from or where it's going to, leave either EO or EF blank, and we'll talk about it. So here's what I think people probably are able to do on their own. And notice that in almost all of these, except for this one, we had a little trouble identifying one of the energy types. And there's a couple things going on here. On the previous page, we really focused on the universe, all the energy there is everywhere. In this case, I wrote these to really kind of focus you on individual things. So like the cart, like the textbook, like the spring. So we're not as focused now on everywhere, we're focused on an object. So we have to talk about how energy can enter or leave the system. And the way it does that is through two different energy types, energy transferring types. Work, which usually gets abbreviated W, and heat, which gets abbreviated Q. In this class, we're going to worry mostly about work. In chemistry, you're going to worry more about heat. We'll also focus on both if you take second year physics, like AP Physics 2. So let's talk about how we actually add energy to the system. In this case, you're sliding something across a table. So what are you doing? You're putting a force on it and you're pushing it through a distance. And that's what we consider to be work. It's applying a force through a distance. So the equation, which we'll get into in more detail in a future lesson, involves both force and distance. So where did the energy come from to give a cart energy as I push it across the table and it starts moving? It came from work. Let's say I slid a textbook across the table. I also did work. But instead of that energy staying in the textbook as kinetic energy, it becomes thermal energy. We could also say, if we just wanted to focus on the textbook, we could say that that energy left as heat. So in other words, we had a transfer out of the system. The energy came into the system from outside and it left the system to outside. Why can I lift something up? Because I'm doing work. This one's kind of a trick question. It seems like if you sit there and hold something for a long time, it seems like you're doing work, but you're not pushing it through a distance. So you're not doing any work. And if you think about that book, if it's just sitting here for 2 minutes, it's not really changing. So it doesn't gain any energy, doesn't lose any energy. So in this case, nothing really actually happens. You get tired because your muscles are twitching and they're doing work in your body. But as far as the book's concerned, no work's getting done. You're doing work here. You're doing work here. Magnetic energy is not something we talk about very much, but as you pull a north and a south apart that tend to go together, you are doing some work. And if you let go, that energy will come back as kinetic. Static electricity, similarly, if you have two pieces of clothing with opposite charges that tend to go together, you have to do work to pull them apart. And they're gaining electric potential energy as long as they maintain their charges. Boiling water, you're putting in heat. And burning some gasoline, heat is leaving. So hopefully what you got out of this is that EO equals EF is true for a system or an object, just as true as it is for the universe. But we have to take into account that energy can enter a system or leave a system. So if it enters the system by putting a force on something and moving in a distance, or leaves it the same way, that's work. It can also enter or leave through heating. And we can still use EO equals EF as long as we take these energy transfer types into account as well. Obviously, we didn't do any math with this. I think really a first step is just to identify the energy types we're talking about. We'll be doing math soon enough. And a lot of these terms will have their own equations that go